Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering Module 8, Applying Chemical Ideas. I'm going to be focusing on Inquiry Question 1, Analysis of Inorganic Substances, and we're going to be investigating a quantitative technique. The outcome or the lesson intention today is to describe the operations of colorimetry and UV visible spectrophotometry. By the end of this lesson, hopefully you get an understanding of how to analyze and interpret these particular graphs related to these particular spectrophotometers. If you want to do a couple of further reading, these are your textbook references. So let's start off with colorimetry. Let's firstly look at how to process particular data related to it and also the processing of how it functions. So, to start off with, colorimetry is an analytical technique to determine the concentration of a colored ion or compound based on the amount of light it absorbs. Okay? It focuses on the absorption of light in the visible spectra, so the entire rainbow. The color intensity will be proportional to the concentration of the sample. You can see this is sort of a basic demonstration of the colorimetry apparatus. We have our light source, we have the slit lens, this is our filter area, this is our cuvette, which is where we store the sample, and then we have our detectors here. So, how does colorimetry work? It starts off with having a standard white light that has all the colors of the rainbow, because that's our visible spectra. We place it in front of a filter. That filter is specifically selected to be absorbed, okay? That absorbs a particular wavelength of light, and then we can measure the amount of light that was absorbed, let's say using our example here where we use yellow. The cuvette is filled with the solution to be analyzed. They are usually about 1 centimeter in width in all directions, so it's sort of like a rectangular shape, and are usually made for polystyrene, which has very low absorbance. We have our sensor that detects the amount of light that's transmitted by our solution. What we mean by transmitted is going through our solution. Okay, so we have a filter that selects a specific wavelength of light to come through, so it differentiates all the different colors. When that specific color comes through, it's going to be partially absorbed by some of the atoms or molecules inside our sample here, and then what's remaining comes through our detector, and then we can record how much was absorbed in that process. Okay, so again, just a little quick summary for you. We have visible light that is passed through a filter to produce the required wavelength to be absorbed by the sample. So this kind of filter we have here, and this is our sample here. The filtered light passes through the solution and some is absorbed. Okay, so here's some of that color light, in this case yellow light, is absorbed. The colored solution absorbs some of this light. The light absorbed is called the absorbance. So you've seen this term before, so we don't need to go over it again. In terms of setting up a colorimeter, most schools might have a less expensive of a colorimeter, and such instruments do need a little bit of calibration or zeroing, and you can do that with colorless deionized water. So this sets the reading to a zero absorbance. Okay, zeroing eliminates error because even a colorless blanket of cuvette and water can absorb a tiny amount of light. So we want to make sure we don't have any background readings that might be affecting our actual sample, hence why we need to do a bit of zeroing. So we already talked about the setup. Let's talk about this component here, the filter. How do we know we have the correct filter for the investigation we want to do. Firstly, I want to talk about quickly how our observation of light works. When wavelengths of visible light is absorbed by a material, whatever gets reflected or transmitted, that particular wavelength becomes the visible color you see. So imagine you're looking at red, okay? The reason why a particular surface appears red to you is because the blue and green wavelengths of light have been absorbed by the surface, whereas red light has been reflected by the surface, hence that's what you see. Have you ever wondered why particular objects look black? And then the reason why it looks black is because all the colors of the rainbow, all that spectra has been absorbed onto the surface. So what you're seeing here is a tone of all the wavelengths of light absorbed, hence that's why you register it as black, because no colored light is coming back to you. Another example obviously is any white objects. A white object would represent any form of light being deflected or reflected off the surface. So that's kind of your examples that you have here. This is how observing colors work. So how does that work with the filter? So when using the filter, the complementary color to that of the solution is used for the filter. Okay? Now that's a little bit wordy, so let's give you an example to explain what's going on. So imagine you have a blue solution. It appears blue because all the colors have been absorbed. So that could be red, green, red, those kind of colors. Only blue is passing through. So yellow is a complementary color to blue. Okay, so it's sort of away from the other side of the spectra. Using a yellow filter, changes in absorbance of a blue solution can be measured using a yellow reference. So if I increase, let's say for example, if I decrease the amount of yellow I have in my solution, and that technically represents an increase, it's kind of hard to show there, but an increase in the color blue. Okay, so just think about it this way. The reason why colors turn more green, okay, or a lighter blue color, is because there is more yellow light to move it towards the lighter component of the spectra. Okay, if we remove the yellow, okay, then what we have more is the blue spectra, and so that's what we end up seeing. So based on how deeply colored or the intensity of that color, we can also work out the type of color that was absorbed. Okay, so what else can affect color intensity? There's a couple of things. So it can be the chemical nature of the substance. Remember, as we talked about with the transition metals, it can be due to the splitting of the D shell. It could just be the natural composition of where the orbitals are for the atom. The thickness of the sample the light passes through. So if we have a thicker pathway, that can also affect the intensity of the color, or as you can see here. Another way that can affect the color intensity is the concentration of the substance. So what we have here is a highly concentrated solution of, I think it's copper sulfate. You can see it's very blue, and then if we have a more diluted version, it is a lot more transparent in a way, but a lot lighter to be more exact. So that gives you an idea of what can affect color intensity, and then obviously the amount of absorbance. If we're trying to graph it out, we use a calibration curve. So we've talked about this before, but on the horizontal axis here, we use a range of highly accurate solutions of known concentrations of a desired metal. So in this case, we're using copper. We have the vertical axis that measures the amount of absorbance at each specific concentration. And you can see that you'll need to do this a couple of times to provide reliability to your curve. And we say it's a curve because, as you can see, it does kind of duck off into a little plateauing spot here. which is also why we never try and predict absorbance that's outside the line of best fit, meaning by we never try to extrapolate because extrapolation is quite inaccurate. We tend to interpolate, so using specific points on our line of best fit to work out what the concentration might be, or might be the absorbance. So it's good at telling us what the concentration of an unknown ion is, so long as we do interpolating rather than extrapolating. There are some limitations of colorimetry though. If we have a cleared or light colored solution, it is quite difficult to investigate. So to get around that, for example, let's say blue, hexa aqua, copper 2 ions, you get this really light blue color. Now obviously the light blue color means that there's less absorbance of the other wavelengths of light. It can also mean that it's a lot more difficult to detect any absorbance. So we can do ligand exchanges to make the color more intense. And by making the color more intense, we get a more accurate reading because we can measure more specifically the amount of absorbance that's going through. So we can replace it with ammonia, as you can see here. Gives it a much more darker blue color. And if we have similarly colored chemicals, that can also introduce errors, as every ion's absorbance does vary slightly. So if we have a very similar color type of chemical, you might assume that it could be one particular type of metal ion, but it's actually the other one, and that can obviously disturb what you were thinking of as your predictors. Okay, the next one we're going to talk about is ultraviolet visible spectrophotometry. That's a very long word, but let's have a look. This is just the general structure of what it looks like. You can see there's a slight difference in the setup to a colorimeter, and that's kind of more so in the first half of the setup. So again, it's an analytical technique to look at colored compounds and ions, but the main difference is it's using a much bigger range. So colorimetry used visible light, ultraviolet visible, given in the name, it measures from the ultraviolet spectra all the way to visible light. So you have a much wider range of light frequencies to use. So components of the UV visible spectra, we have these components here. So we still have a light source. We have a thing called a monochromometer, which is just to ensure that only one wavelength of light will be passing through. We still have the sample, we still have a detector in it. So the main difference between colorimeter and a UV spectrophotometer is the monochromometer you have there. So the chromometer replaces the filter to select a light of an exact wavelength to be used in the analysis. Any substance which dissolves in a solvent and absorbs UV or visible light can be analyzed using this method. So we're trying to be a lot more precise with the specific wavelength we want to see, and also we also can look at the UV spectra of light as well. So if we look at the different components, we have the light source that's made out of deuterium, which gives the ultraviolet spectra of light coming through. We have tungsten, which gives the visible spectra of light. So that gives you a nice range of 200 to 800 nanometers. We have a monochromometer, which uses a diffracting grating. Now a diffracting grating basically, as you can see, sort of an example, but it basically splits the wavelengths of light into different angles. And by moving your detector or using a particular slit to select which angle of the light coming out you're going to use, you can specify the type of wavelength you are going to try and measure for absorbance. We have a reference cell, so that's one where we have the pure solvent. So if you look at our setup here, we can see we have the reference cell. That's the sample where we can obviously do our zeroing or calibration, so we know what the background info or background data is, and then we have the sample that we have there. We have the actual cell that holds the sample, and then the detector that calculates the absorbance comparing light. Okay, so if we look at the ultraviolet visible curve, we can actually use it only for inorganic compounds. We can also use it for organic substances as well. So we have butyl 1,3-diene, which is colorless. Now the reason why it's colorless, if we actually look at the curve in terms of wavelength to absorbance rather than concentration, we can actually see that the maximum absorption of light occurs at the about 217 nanometers. So that's in the ultraviolet region here. So that means that any light that's coming through would not be visible to the to a normal colorimeter, but obviously for our particular apparatus here, it can detect that. And then the next one we have, also forgot to say, this also explains why the compound would be colorless. As you can see, the wavelengths of colors aren't existent there. So that's kind of one of the applications of using UV, because we can see absorbance that wouldn't normally occur if it was in the visible spectra. We can also see, if we're looking at the actual visible spectra, so the colored rainbow for copper, we can see maximum absorbance occurs where the yellow is. So that's where the greatest amount or increase, or where we begin to see an increase in absorbance of light occurring for copper, and that explains why it would appear blue. Okay, so let's just quickly look at how it works. Alright, so big slide. Thank you for the colleagues here for helping out. So the light source is a combination we already talked about of tungsten and deuterium. And so that provides our particular, light source of not just color light, but also the UV spectra. We go to the monochromometer, which splits it into the specific wavelengths that we want. There is a spinning disk of transparent, opaque, and mirrored surfaces, splits the light beam which travels through the sample. The samples are held in optically flat, transparent containers called a cell, cuvette. So that's the, as we've talked about, the thing that's storing the sample. The reference contains the solvent in which the sample is dissolved, and this commonly refers to as the blank. For each wavelength, the intensity of light passing through both a reference cell, we represent as I0, and the sample cell is measured. The detector converts light into a current. High current would equal high intensity, and the chart plots the absorbance against wavelength, which is what we saw here. And obviously that would explain to us where we would see maximum absorption. So this can actually be represented by the Beer-Lambert's law. This isn't stated specifically on the syllabus, but it is quite crucial to remember this formula here. So it explains that the relative amount of a particular wavelength of light being absorbed is represented through this formula here. A, capital A that is, represents absorbance. This epsilon sign here, that represents molar absorptivity, so the chemical's ability to absorb light. Lowercase l, that represents the path length, so you can see represented here as B, that is the path length that we're talking about. We have C, that's the concentration of your sample, and then I naught is the intensity of the incident light, and intensity of the resultant light is this one here. And so that gives us a nice little equation. As you can also see, absorbance is directly proportional to the concentration. So if we're increasing the concentration of iron as we go along here, you can see with this intensity of light, absorbs a lot more of the light of the bluer colors than our lighter colors here. So this is absorbing a lot more light. That's why we see a much more distinct color. This has a lot more sort of diluted transparent color, and so that means a lot more of other wavelengths of light are coming through. That's why we can't really make out as clearly what the distinct color would be. Right, when it comes to determining the sample, again, we can plot a absorbance to concentration graph. Same thing as before. The increase in concentration, as we said, would be directly proportional to an increase in absorbance. What we need to do is, with a known sample of a known concentration, make measurements as a reference, and then we can, for unknown solution, measure the absorbance and then interpolate to work out the concentration of that unknown solution. So let's, for example, use this question here. So the concentration of iron in a dam water is determined by a colorimeter. The absorbance of a series of standard solutions and a sample of dam water are shown in this particular table. Determine the concentration of iron in the sample. What you need to do is graph this out, concentration over absorbance, or absorbance over concentration, sorry. And so this is the graphs that you can get, okay? So drawing the graphs here, you can see that if you plot, which is saying determine the sample, so the sample has an absorbance of 0.38. So after you've plotted the graph, interpolate 0.38, drive it across to your line of best fit, take it down, and you can see it's around about 9 milligrams per liter. So same idea as when we did the atomic mass spectrometry with that, or absorption spectrometry, sorry. Alright, just another question that you can have a look into, read through. You can pause it here and I'll show you the answer. Alright, showing answer. So again, you just plot it out and you should get approximately this number here. Obviously it might change or fluctuate depending on the line of best fit you create. Alright, so that concludes our lesson for today. We've basically covered colorimetry and also the UV visible photospectrometry. So that gives you an idea of how we can actually measure the concentration of colored solutions. If you found this video useful, give it a like, give it an encouragement, and as always, take care and have a great day.